And thank you for joining us in celebrating what is a truly remarkable event here at the University of Montana, the recognition of Professor Steve Running as a Nobel recipient. My name is Royce Engstrom. I'm the provost here at the university, and it's a true honor this afternoon to be able to introduce Steve. Before we do that, though, let me ask you to just check your cell phones and make sure that those are off, if you would, please.
Geez, I don't...
On October 4th, 2007, the Nobel Peace Prize was awarded to Al Gore for his work in educating the world about global climate change. And simultaneously, the prize was awarded to the International Panel on Climate Change for its work in articulating the scientific basis behind the causes, impacts, and mitigation approaches associated with climate change. As all of you know from the press, Professor Running was one of the lead authors on the North American section of what is called the Fourth Assessment Report. The university's only other association with the Nobel Prize was when UM student and instructor Harold C. Urey went on to win the Nobel Prize in Chemistry in 1934. Before introducing Professor Running, I would like to tell you a little about the International Panel on Climate Change, or the IPCC. The IPCC was established in 1988 by the World Meteorological Organization and the United Nations Environmental Program. The membership on the IPCC includes world's leading researchers in climate change, such as Professor Running. Those researchers contribute to the assessment and the critical analysis of any and all available information related to climate change. The report, the Fourth Assessment Report that they just put out, serves as an unprecedented call to action for the entire human race. Steve Running is a professor of forest ecology in the College of Forestry and Conservation here at the university, having joined the university in 1979. He also directs the Numerical Pterodynamic Simulation Group, whose mission is to describe quantitatively the structure and function of ecosystems. Professor Running has carried out pioneering research in forest ecology since before his arrival at the university and has published over 200 works on various aspects of ecology, including, of course, the impact of the response of ecosystems to climate change. He holds a bachelor's degree in botany and a master's degree in forest management from Oregon State University and a PhD in forest ecophysiology from Colorado State University. His work and that of his co-workers and students is funded and supported financially by NASA and the National Science Foundation, among other groups. Professor Running has been appointed to an extraordinary array of national and international committees on ecology and climate change, in addition to his work with the IPCC. Some of those appointments include appointments by the prestigious National Research Council. In addition to his work as an internationally known scholar, Steve is dedicated to making sure that the University of Montana students are educated in the challenges of climate change. And he has recently agreed to co-chair a special task force to develop an interdisciplinary curriculum on climate change. So we're very fortunate today to be able to recognize Professor Running and to listen to his address, 5 Stages of Climate Grief. Be sure and stay afterward and attend the reception if you would, and talk to Steve one-on-one if you have questions or comments. Would you join me now in congratulating and welcoming Professor Steve Running, Nobel recipient.
All right. This mic going? Yep, it is. So I kind of watched as everybody came in today. You ever notice how both at church and at typical university classes, the back fills up first and the front rows are all empty until there's nothing left? And of course then when Mick Jagger comes to town, everybody pays the biggest money to sit in the front row. So I thought, all right, this is a test to see if anybody sits in the front row. Well, I want to start before I get to the science I'm here to summarize with just a statement of the two women that keep me functional. And Dr. Young-E Cho, my program manager, is still in Korea and won't get here until Wednesday. My wife, Connie's right here in the front row. I wonder why she always looks so somber when she's out with me. I don't get it. But a number of people in this city think that I'm the husband of Connie running, and they don't much know what I do, because she does quilts like this by the dozens, and they're an absolute kaleidoscope of color, and I never was sure if that was her artistic intent or whether the fact that I'm colorblind, she was just trying to make it bright enough I could see it. But I better get on to my task at hand. And here is the text that the Nobel Committee put out. And the Nobel Peace Prize for 2007 is to be shared in 2 equal parts between the Intergovernmental Panel on Climate Change and Albert Arnold Gore, Jr. And the answer is no, I don't get any of the money. And you can see further their statement for their efforts to build up and disseminate greater knowledge about man-made climate change and to lay the foundation for measures that are needed to counteract such change. Now, one of the things I had a number of emails in the days right after this announcement challenging me as why the IPCC should get a Peace Prize. And for these people, I sent them this report that came out just last spring. This was a Pentagon report by 11 retired admirals and generals. And they summarized that projected climate change does pose a serious threat to America's national security. Climate change is a threat multiplier for instability in volatile parts of the world, and even in stable parts of the world. It will add to tensions that already exist. And they summarize a recommendation fundamentally that the U.S. should commit to a stronger national and international role to stabilize climate change. And so this isn't a stretch one bit for IPCC to be given a Peace Prize. Climate progressively in the coming decades will be a source of war and peace tensions. Now let me give you a little more summary of what the IPCC is about, just real quickly. It was formed in 1988. The big assessments, of which ours is the 4th, the first one in 1990, then 95, 2001, and now our 4th. And our job was to summarize and assess current literature and current research understanding on climate change. We didn't do any new research at all. We weren't paid at all for this. This was part of our professional responsibility. And what we wrote went through a 3-stage review process that was much more like a legal cross-examination than it was typical journal peer review for the kind of academic writing most of us do in a university setting. It was really something I had never seen before, where every sentence I wrote, I had to be able to document or else it'd be taken out. And note finally, the IPCC reports are policy relevant, but not policy prescriptive. There's 3 working groups. The working group 1 is primarily the physical climate. Working group 2, what I was in, was the climate change impacts and adaptation. and then working group 3 is mitigation. So there's 3 sections to this overall assessment. And so you might see there have been pieces of this report coming out since February, and the last summary for policymakers just came out a week ago. So this isn't actually one single document. It's a continuing stream of documents that collectively is this overall assessment. And an incredible range of people involved, ultimately. There are 2,500 expert reviewers from governments and entities around the world, 800 contributing authors. I was part of the 450 lead authors that actually wrote the document from 130 countries. And overall, 6 years of work. The big climate modeling center started the global climate runs for this in 2001. So we would be ready in 2004 to start our assessment. And all this funnels down to finally these reports now in 2007. So my part of this started in Vienna at the United Nations Center there in 2004, and this is where my role in this began. So that's the summary of basically the organization and the report. Now on to the science. And for those of you that have heard my talks before, I have at least a dozen new slides in here I've never used. And I'm getting a little nervous in a town the size of Missoula that everybody's heard this one before. So there is new things, so don't go to sleep. But I have to start with a couple of critical principles of earth science that I think are widely not understood and really important. First is the simple difference between weather and climate. When we watch the TV news and weather at night, and they forecast what's coming over the next 5 days, the snow that's supposed to arrive here tonight, that's weather. And that comes to us basically directly from the atmosphere. That's what delivers the weather, is the atmosphere. But climate is a lot different. Climate is asking, are there trends going on over decades to even centuries that are pushing the weather in a certain direction? And so you might think of following the Dow Jones Industrial every day when it's up 200 points one day and down 200 the next, versus trying to use it to see the trajectory of the national economy. And then it's a similar sort of analogy to when we're looking at trends of climate. We have to look at least 30 years before we can be legitimately looking at a climate trend. 1 or 2 years is just a noise to us. The second basic principle that's not unrelated is the role of the atmosphere. And I like to take claim to the Mount St. Helens eruption that we had just got here a year earlier. So, and a number of you, probably, how many of you are here for Mount St. Helens? Probably an awful lot, yeah. And so we all know that we got about 1 centimeter of ash right here in Missoula. And do you know that about 12 days later it came back again? And we got a second layer of ash. Now, it was almost imperceptible, so probably you didn't notice. With research instruments, we could. But that showed in a simple way, a very fundamental principle. It only took 12 days for that air to go around the entire planet at our latitude. 12 days. So when you see a 5-day weather forecast on TV, what they are forecasting of the air for Saturday is right now out in Siberia somewhere, halfway around the world, on our way towards us. And the more fundamental principle here is that the atmosphere doesn't have very much memory. It really doesn't carry very much memory of the climate of the Earth. And we understand that now much better than we did 30 years ago, that the atmosphere delivers the day-to-day weather to us, delivers climate over time, but it isn't what produces the climate trends. And we now know that it's the ocean, land surface, cryosphere, total Earth system that defines the climate trends that we're looking for and are important for these questions. Now, this whole topic started with this one graph. This one graph. The CO2 measurement from the Mauna Loa Observatory in Hawaii. Charles David Keeling there on the chairlift with me going up Snowball only about 3 years ago. This is, in earth science, this is iconic. The Keeling curve, you don't have to say another word, and everybody knows what you're talking about. The important thing that makes this curve so really iconic is that it was the very first time we got a sense that humans could impact the entire world. Up till then, we really thought we were tiny little ants on a giant Earth. And this graph was a forewarning that humans had the capacity to influence the entire Earth system. It was only the first of many, but it was the first one, and when I think back now, it woke up the scientific community 20 years early to global research that otherwise would have taken a long time coming. So when I started on this in 1981, it was a direct result of the scientific community getting started on understanding the Keeling curve. And you'll notice that ever since the first year, CO2 in the atmosphere has gone up every single year. Not 1 year has it even stayed level. You also notice that from summer to winter, there's an oscillation in the curve. And that is a first look for us of how the biosphere interacts with the atmosphere. We'll talk more about that in a minute. All right, why do we care about CO2 in the atmosphere to begin with? Well, this isn't new science at all. This guy, Svante Arrhenius, in 1896, matter-of-factly just put 2 and 2 together and figured out that humanity was starting to burn more coal for heat in Europe, and that was producing CO2, which was a greenhouse gas, and sooner or later the Earth's going to start warming up. He figured this out 100 years ago. So this is not glorious new theory we're pursuing at all. We are simply documenting the prediction that he made a long time ago. So how are we doing in these CO2 emissions? And this is one of the graphs that makes we IPCC authors most nervous, is when we started the climate model runs for the report in 2001, they built these scenarios of CO2. These funny or letters here are just the shorthand for scenarios of how rapidly humanity would emit CO2. In effect, what kinds of coal burning, oil burning, gas burning, what would be the emissions rates with different types of economic development. And there were all these scenarios, and some of them very aggressive, some of them putting in a lot of conservation principles. And what we find ominous is this is reality right here. We are currently going higher than the highest emission rates that were projected. These last few years, we just see global CO2 emissions, the lid just blowing off. And this, you can't understate the significance of where this is going to take the Earth system if it keeps up for very long. Now, where does this CO2 that gets emitted, where does it go? Well, it turns out only about half of it stays in the atmosphere. At the moment, the oceans and the land each remove something on the order of 25 to 30%. And this is a point of of continuous sport between the ocean and land scientists. You can tell this graph was built by land scientists because that puts us ahead. And if I was an oceanographer, they would have these numbers probably about reversed. And the real answer is we don't know exactly where all this CO2 goes. We can measure the atmosphere very accurately, so we know how much remains in the atmosphere, but we don't know entirely where the rest of this carbon's going. And that's part of trying to understand the whole global carbon cycle. And of course, an important corollary to this is if either of these sinks gets weaker, then CO2 in the atmosphere goes up even faster. All right, if there's one summary slide for our fourth assessment report, it's probably this one. And it shows the acceleration of the global average air temperature. And it particularly shows that in the last decade or so, we seem to be just virtually breaking a new record every year. And these are temperatures that are higher than any in the last 1,000 years in the Earth record. And we just relentlessly are increasing every single year is at or near a new record. Now, it's important to analyze what we think we understand about how the carbon emissions actually relate to the air temperature. And so in the climate modeling, what they have found with these climate modeling groups is that the only way they can accurately simulate this acceleration of air temperatures in the last 25 years is by adding the greenhouse gases and sulfate aerosols from fossil fuel emissions. If they just run the models as if humans were not on Earth, they would not be able to, they recreate the early part of the curve fine, but they don't recreate this last 25 years. And one of the big parts of our understanding that's improved so much since I was in graduate school is we now have much deeper understanding of the role of the oceans. We now realize the oceans function as this long, slow conveyor belt. Some estimates are that the ocean circulates around the planet in 1,000 years or something really long and slow, but carrying a tremendous amount of heat. Water has a very high heat capacity. When we get a forecast for an El Nino or a La Nina year, what they are actually referring to when they announce an El Nino is on the way is they're measuring ocean temperatures out by Tahiti and Fiji. So we know now in a way we didn't 30 years ago that the oceans carry the climate much more, an order of magnitude more than the atmosphere. And in fact, a paper in Science itemized this and tried to analyze over the last 50 years where all the additional heat energy had gone from greenhouse gas trapping, heat trapping. And they looked at glaciers, and they looked at Antarctica, and they looked at the atmosphere, and look at the big number. 90% of that heat content turned out to be in the oceans. And in fact, it was Jim Hansen's climate model, Jim, that was here just about a month ago for our presidential lecture series. It was Jim that figured this out with his GCM. Now we know the oceans are warming up. We have satellite data that measures sea surface temperature. They've been up since 1979, and you'll notice every single ocean basin is warmer by at least a couple of tenths of a degree. Now, one of the things warmer water does is it expands, and so the biggest issue in our final fourth assessment summary was what rate of sea level rise do we think is going to be occurring over the next 100 years. I think also, quoting Jim Hansen, he feels sea level rise will be the single most damaging part of climate change to humanity. The single biggest impact he feels will be sea level rise. And so looking at this graph, the satellite measurement of the rate of sea level rise since 1994, you see a very continuous, very high precision measurement. These satellites measure the sea level to accuracies on the order of tenths of millimeters. It's really incredible technology. And so we have a very good measure of the rate of sea level rise. And in our final fourth assessment report, we put the window of best estimate at somewhere between 40 and 70 centimeters of sea level rise over the next 100 years. And the ink wasn't even dry on the report. And papers came out suggesting that was going to be too low and that it might be more like 70 to 90 centimeters. So this is a topic that is absolutely in the Earth's system science realm. This is one of the biggest topics around, is what is the rate of sea level rise that we think is coming. Now, another aspect of the ocean system we have to pay attention to is acidification. As CO2 increases in the atmosphere, some of that CO2 dissolves into the water, turns into carbonic acid, and literally makes the ocean more acidic. And we now have a measurable decrease in the pH of the atmosphere. Now, the most obvious reason why that matters is the calcium carbonate that forms coral reefs and shells of shellfish is dependent on the dissociation constant of pH of this water. Some of the estimates I read, and this certainly isn't my field of expertise, is that within something like 100 years, our coral reefs won't be able to grow anymore purely due to the chemistry of the ocean water. Purely due to the pH of the water as it goes down reacting to CO2 in the atmosphere. Now, it's probably a more common ocean topic that probably everyone here is familiar with is increases in hurricane intensity. And 2 years ago, right in the middle of Hurricane Katrina, big papers came out in both Nature and Science from 2 separate labs suggesting for the first time that there looked like a correlation between increasing sea surface temperatures and increasing hurricane intensity. Not the number of hurricanes, but the intensity of those hurricanes when they occur. And people like this year said, oh, gee, this wasn't a very bad hurricane season. Well, what they don't know is this was actually above average hurricane season by a little bit, but none of them hit landfall, so it wasn't in the newspapers. So you really can't judge the hurricane dynamics by what you read in the papers. Imagine that. But we have very clear evidence, and this is a topic of intense, obviously intense analysis, is how much of increasing hurricane intensity might be driven by warming ocean temperatures. And of course, we also have billions of dollars of more real estate along our coastlines, so there's much more infrastructure at risk than there was 50 years ago. And so we have to separate the socioeconomic part of this question from the purely climate part. Is global warming increasing hurricane intensity? And right now, the overall consensus is at some level it is. Now, if we go to the other end of the ocean, so to speak, and we look at the high Arctic, we have very clear evidence that the Arctic sea ice is getting thinner. Our best early measurements actually came from the U.S. Navy. In 1957, when the nuclear submarine fleet was deployed, the Navy started measuring the sea ice thickness all across the Arctic. And so we have tens of thousands of measurements from 1957 on. This is a measure, if you can see here, of a satellite measure of Arctic sea ice. And we've basically lost about 2 Montanas of area in sea ice area. And we've lost in thickness from 9 feet down to about 5 feet in thickness. So these are numbers we really know quite well. Another cryospheric measurement that we watch really carefully and have the ability to watch carefully is the Greenland ice sheet. And we have radar satellites that can look through clouds, and we can track the summertime melt of Greenland. And it used to melt out, the edges would melt out around there, and this red denotes the difference from the melt back in 1992 to the melt in here in 2005. And you can see a dramatic increase in the area of meltback in Greenland. And what hasn't even hit the graphs yet is 2007 set a new all-time record low for this ice melt. And so I don't even have a graphic on that yet, because that news is only a few weeks old. Now, if we go to the other end of the planet, we see the same thing. The West Antarctic glaciers were measured at 5-year intervals, starting, you can see, back in the 50s. And they used to be getting a bit bigger. And starting in about 1970, every single 5-year increment has been down. Every single one. Not one increment has been up. And of course, all we have to do is come right back to our own backyard in Glacier National Park. Shepherd Glacier in 1913 and 2005. And probably most of you have read from Dr. Dan Fagery up in the park that just finished a new analysis only about a month ago that he now projects all the glaciers will be gone by 2020. He used to say 2030, and now he's changed that to 2020. I find it interesting that when I speak around the country, that is a very iconic statement. No glaciers in Glacier Park just hits people. I can talk about dozens of other slides and they kind of nod off, but boy, then you say no glaciers in Glacier Park, and it's one of those things that people remember. Let's look at some biospheric responses, some of the things I put in the IPCC report. One of them, for gardeners in the audience, things are looking up from Montana point of view. The growing season is getting longer in Missoula, a couple weeks or so longer. The period of frost-free days is getting longer, and this graph from this one paper shows all through the West a very consistent trend of longer growing seasons and earlier spring green up over the last 50 years throughout the West. You notice not very much in the difference in the Southeast. And one of those aspects of variability of climate that makes this a challenging topic. Now, the impact that is our sea level rise is this one. This is what our wildfires look like in mid-August from the space shuttle. And I can't even figure out where Missoula is in here. It's such a weird oblique angle. I've looked at this thing every which way. And NASA provided this georeference point to Livingston, so that's what you get. But look at the plumes, what these look like from 100 miles up. And of course, we were down under them, so we know absolutely how heavy and how thick this smoke was this year. And of course, in recent papers, particularly, we had papers in Science in 2006, and the cover photo, which everybody always wants to get the cover photo, and you never know if you're going to get it until the issue hits the streets. But the Western fire season, on average, is now something like 78, 80 days longer. And there was a wildfire in Montana just 4 days ago, wasn't there? That never used to happen. Mid-November, and we're still having wildfires. In California, there's one going right now. That didn't used to happen. So we're absolutely seeing the fire season of the West getting months and months longer than it was 30, 40 years ago. And of course, a number of our students make money fighting these fires, so they're probably, some of our graduates are on these fires right now. Well, we know that the fires, there's been a fourfold increase in major fires over 1,000 acres. We know that there's been a sixfold increase in the acreage burned in these big wildfires. And we also know a curious point, this is from Tony Westerling's paper, that the biggest increase is at higher elevations. It's not down in the valley bottom Ponderosa Pine where we think historically about fire in the west. It's the higher elevation stands that used to have snow cover. And when there's snow on the ground, a forest doesn't burn. And so I've, in my IPCC analysis, put together this story, for lack of a better term, of how the fire season is now being pushed forward in time by earlier snow melt, and we then have a longer fire season that's both drier and longer and covers higher up into the mountains to areas that didn't used to burn. When I was a kid growing up in Seattle, if you wanted to go hiking on Mount Rainier, you didn't even bother thinking about it until mid-July because the snow was 10 feet deep. All right, let's take a look at some of our climate trends closer to home, and let's start with ocean temperature. Since I've made such a big deal about the oceans, well, here's the news. Back when I was in Seattle swimming as a kid, it appears like it was 48 degrees. And I wasn't very smart, clearly. Somewhere around 1980, up started the ocean temperatures. And we see now a 2 degrees increase. This is where our daily weather comes from. This is straight upwind from us, the ocean that's most directly impacts our weather. And that's a pretty substantial increase in not very many years. Now, if we look at the pure weather station temperature record, on the order of 1 to 1.5 degrees Fahrenheit increase over, this is analysis was from the Climate Impacts Group in Seattle, and they started at 1920. So over about an 80-year period, on the order of 1.5 degrees overall. And you see how consistent this is. Almost every station in the whole Northwest shows this trend. One of the most immediate effects of this warming temperature is that more of our annual precip is coming as rain and less of it is coming as snow. And we're going to talk about more about that in a minute, but I think this is a trend we're already seeing in Missoula. And you see that we share that trend all around the West. There's an awful lot of areas. All those red dots are more rain, and the blue dots are less rain. But this graph, the first time I saw it about 4 years ago, is the one that I found most unnerving. The USGS used to define April 1st as the peak of the snow year. That was basically the end of the winter. The snowpack was as deep as it was going to get before it started melting. And so they've measured April 1 snowpack very carefully for a long time. And so you see since 1950, on average throughout the Northwest, 30 to 40% lower April 1 snowpack than we had 50 years ago. And this graph, I gave a talk at the Lewis and Clark Festival this July over in Great Falls. And as I was reading up about Lewis and Clark, of course, which I have to confess I hadn't done quite enough homework beforehand until the last month, and then I crammed just like an undergrad. It was pathetic. I was reading night and day and drinking coffee. No. But the thing, as I read through the whole amazing story, which we all know just how astounding the overall story was, from a climate point of view, one fact just hit me like a hammer. On June 21st, as they were coming back in 1806, They are trying to come back over Lolo Pass on June 21st and were turned back by 12-foot deep snowdrifts. Now, when our IPCC report came out, one of the local news stations, we went up into the Bitterroot on April 6th. And I was standing at 6,000 feet on a north-facing slope, and there was nothing more than a skiff of snow left. And Lewis and Clark, 2 months later into the summer, were battling 12-foot snowdrifts. And so our snowpack is clearly on the way down. And we know this from a different measurement also. If we look at the timing of river runoff, which are rivers peak at the peak of snowmelt, throughout the Northwest, they're on the order of 10 days, 15 days, even 20 days earlier than they used to be. So a completely separate measurement. Now, as I've dug deeper into this early snowmelt question, here is another interesting fact that came out. The trends of March temperatures around the state. And so this is, you'll notice, since 1950. This is Bozeman, Billings, Kalispell, Great Falls, Missoula. And you see the overall trend line headed up. And all of these stations are on the order of 5 to 6 to 7 degrees Fahrenheit warmer in March than they were 50 years ago. You know, in climatology, we usually talk about tenths of a degree. We don't talk about 3 and 4 and 5 degrees. This is really remarkable. And when you think about what's going on, this incidentally is our MODIS satellite that our lab has been part of for almost 20 years now, and this is how our satellite sees the western U.S. in the spring snow cover. So you can see Flathead up here, and we're looking all the way down the west coast. So this is basically the whole western U.S. And one of the things that's very striking, whenever there's snow on the ground, you have a surface that's about 60% reflective. The minute that snow melts, that surface goes from 60% reflective to about 10 or 15% reflective. All that additional energy stays on that site for every single day afterwards, from the day that snow melts. And so that really is a switch in our springtime climate that I think is being switched so much earlier that we're seeing this amplification of temperatures that are really quite remarkable. And of course, if you don't have any sort of theoretical interest in this, and your interest is how long your season pass at Snowbowl is going to last, the news isn't good. The snowpack right now, here is 2005, basically comes down to the bottom of the valley. We attempted to drape onto the topography the projected snowpack for 50 years from now. Admittedly an imprecise estimate, but here's what we came up with. Okay, here's the lodge right here. So right here you take your skis off and you start walking, and you can walk the rest of the way to the bottom of the hill, and this is in March. And so it doesn't look good for 50 years from now for March skiing. Now, when we look at annual mean temperatures, it's about what that Seattle group found, on the order of 1 degree to 1.5 degrees, except for in Great Falls, where they kept moving the station, and so the records are really corrupted. And this is part of climate science. Now, what they did 50 years ago with the weather station impacts whether you can do any good science with it today. Our total precipitation trend is very hard to interpret. In the 5 stations that I have here, a few of them have gone up maybe an inch in the last 50 years. A few of them have gone down an inch or so. And obviously, we all know there's huge variability from year to year. So all of these subtle trends are masked by normal precipitation variability. And there's hard to draw any conclusion from that. But what isn't hard to draw a conclusion of is the annual snowfall. And even looking at, this was our 1997, we all remember that winter, the snowfall trend in every single station is down. And in Missoula is down on the order of 22 inches from what we had 50 years ago. And it implies, at least roughly, that in 50 years or so from now, we won't get any snowfall at all in Missoula. Now, one of the next impacts from this early snow melt, and I really felt bad that for the IPCC writing I did not have good enough papers to document to the level of rigor that passed IPCC tests, so I wasn't able to write this the way I think is needed, is that there's sure suggestions that as our snow melts earlier, this is the hydrograph for the Missouri River over in Great Falls, and here's the long-term average with the peak in the spring, and then this is 2004, and sure enough, or 2003. It seemed to peak a couple of weeks earlier, much like the trend we're seeing. The peak isn't what I'm worried about, though. It's down here come the summertime, the low flow at the end of the year, where the low flows used to be dramatically higher than they are now. And think of how many of our trout streams were closed to fishing for weeks and months this summer. And it's all because of low water flow in the streams. And so I'm seeing ominous signs that this sort of trend is on the way, that we're running out of water in our streams in late summer, and it's starting with that earlier snow melt. Now, another impact that is getting started from these longer, nicer growing seasons and easier, earlier snow melt is big forest epidemics. And this is the mountain pine beetle epidemic up in British Columbia, and I really need to take myself a field trip because I haven't been to see this, but this was their map in 1998, and look at by just 4 years later, it just like a bomb's gone off, and I guess you can just drive for kilometers up there, and just kilometer after kilometer of dead forests. Well, the reason for these forest epidemics is complex. It isn't a simple cause and effect relationship. But one of the things we know matters is cold winter temperatures. And not so much average temperatures, it's really some occasional extreme days. And you can't say that we liked it when it was 20 or 30 below zero, but it actually has an important ecosystem cleansing role to hit those minimum temperatures. And it kills bugs by the zillions. And what we're seeing now, this is the Missoula, the count of the number of days per decade where it went below 0 Fahrenheit. And so you see on average, we used to get something like 100 days a decade, or about 10 days a year on average, that went below 0. And I think all you veterans around here, yeah, that sounds about right. Well, look what's happened in the last decade or so. We're down now to where we only have a couple of nights below 0 every year. And for just year after year in this last decade, this is pretty much true. We're not getting the 15 and 20 below 0 weather we used to. I remember one week where the high for the week was below 0. For the entire week was below 0. We haven't had anything like that in a decade at least. Maybe this winter will be it. We really need to tip this back a little ways. And it seems a little ridiculous to hope for minus 20 weather, but we kind of need it to slow down these bugs. And then let's talk about July. And of course, 11 days over 100 degrees in 1 month. The decade of the 90s, the whole decade didn't have that many. And so this from our our Weather Service office in Missoula, the summary they put out, along with the all-time high temperatures for both night and day, that 11 days over 100. Now, if you're sharp, if you haven't fallen asleep yet, you ought to be thinking, hey, wait a minute. I thought he said weather and climate were different. Isn't he talking about weather all of a sudden? Was anybody thinking that? Oh, you really are asleep. All right. Well, you should have been thinking it. But there's a reason for me to focus on July of 07. And that reason is that the climate models project in 50 years that'll be an average July. This is a bit of a complicated graph, but it's the single most important projection for the future I have. This is straight from our IPCC report, climate model runs. And you see I picked out the western US, western North America, and for about 40 years from now, these are approximate times obviously, and these are all different climate models. This isn't just one model, and that's important. These were 7 different models run in different countries. And they all agreed that overall we're going to be 2 or 3 degrees centigrade warmer in the winter with hopefully 10% more precipitation. I hope that's true, but the summer really looks grim because all of these models project 3, 4, 5 degrees centigrade warmer, which is just about what July 07 was compared to normal. And not one of them projects any more precip than we get now. All I have to do is put those 2 facts together, and I can just guarantee we're going to aridify western Montana, kind of heading the direction of Utah is what our climate's going to be doing if these projections turn out to be accurate. And so when we step back to from our local issues now to the global scale, and this is the Earth temperature anomaly over the last 1,000 years. I talked about this earlier, and you see how for the last 1,000 years we sat in this envelope of natural variability, as I like to call it. And the variability went down here when they invented the mercury thermometers in about 1600. And so the Earth didn't change, but the measurement precision did. And so we've sat here for the last 400 years, and here's where we are now. We've gone beyond the highest temperature of the last 1,000 years. But that isn't really what concerns us as IPCC scientists. It's not where we're at now that is all that concerning if it was stopping right now. But here's where we think we're going. With a completely business as usual attitude by humanity for the next 100 years, we imagine we could end up something like there. The best we can do, if we got to work on this issue tomorrow, we're still going to end up here. There's so much heat already in the oceans from the last 50 years that we're going to go this high no matter what. And that's why we can't stop this overnight, even if we all walked home tonight and left the heaters off. And so somewhere in here is our trade space for humanity for global temperatures in the next 100 years. And that's what the IPCC authors are concerned about. We like to think this is still a fairly functional planet. We don't want to make any guarantees if we end up there. So now I get a little social commentary. I figure you only get a bully pulpit every once in a while, and this is what tenure is for, is to say outrageous things. So now's the time. I am still tenured, aren't I? Okay. No! And of course, this is the cover of National Geographic 3 years ago. And we all know that nowadays, almost every day, the price of oil is bouncing between $95 and $100 a barrel. When this came out, it was only 60, and they thought that was a big deal. Well, what's going on? This is a Department of Energy graph that was done showing oil discoveries and then global oil consumption starting in 1930. And you see, back in the good old days, we were finding tons of oil, and we were only using a little bit of it. Well, around 1990, it basically switched. And since 1990, so for a full 17 years, we've been consuming more oil every year than is being found. And so even if you don't believe a thing I've said in the last half hour about climate, we've got an oil issue anyway. And so now, Chevron has an ad in The Economist almost every week nowadays. It's the inside front cover ad. And one of the lines is, we're using twice as much oil every year as we're discovering. How much longer can this go on? Simple as that. And this graph really brings that home. And let's see where it's all going. This is the per person, the per capita carbon emissions by country. And we don't have to even look. I looked and looked for a better version of this graph yesterday, and I couldn't find it. So this is the best I can give you, but we don't need to ask who this is, do we? Okay? And so here's the average of the developed countries. Here's the world average. So what are we, only about triple what the world average is? And so we all know who the big consumer is. You know, China's down here somewhere like this. Everybody likes to talk about China, but per capita emissions, there's no question. When I was in India a couple years ago, we were following this three-wheel auto rickshaw with 13 guys hanging on to this auto rickshaw. I couldn't believe it. There were 5 of them on the outside, as you can see. And every single one of them dreamed about having their own scooter. And as we all know, with the way China and India are developing, they're going to be getting their new scooters, for sure. And so we have an accelerating demand for oil by China and India on top of the current demand, which is already outstripping the supply. I really think the front lines of this issue now are moving past we earth scientists. Maybe I'm trying to get some time to go fishing or something and get a little downtime. But as climate scientists, we've pretty much said all we can say. And I think a next assessment 5 years from now is just going to extend all these graphs 5 more years. And I'm sure there'll be a few more discoveries, but I don't think the bottom punchline is going to change any. I think the action point for this whole topic is rapidly turning to engineering, social sciences, of how to get people to cooperate on this, political sciences, of how to get political leaders to lead in what needs doing. I mean, this is absolutely the impetus behind our interest in developing a new curriculum for U of M that explicitly focuses on the interdisciplinary solutions that are going to be required. And I think this is no longer just a topic for us climate scientists. And we've got a number of big choices on the way. And I've already spoken about water once, and I'm going to speak about it again. If it's 5 degrees warmer in the summer with 10% less rainfall in Montana, something's going to give here. There's either going to be water on the crops, or there's going to be water in the river. But you just go do the mass balance. There won't be enough molecules to do both. So something's going to have to happen on that one. Energy choices are well underway. You know, 2 train loads, not train cars, 2 train loads of coal are burned by Colstrip every day. And I think Jim Hansen was pretty clear about a month ago. He's given up on oil. He says, oh, the oil will be gone. Just don't worry about it. It'll just be gone in a few decades. But coal, we cannot turn and put all the coal in the ground up into the atmosphere. And he was more blunt about that than I even thought he'd be. Now, one of the solutions that's starting to bubble up is biofuels. And whereas I think Montana is in a pretty interesting situation to be a biofuel producer at some level, it's going to be hard to make the right choices. And one of the choices we already know isn't right is to use food corn and make ethanol out of it. That is not the answer. And it's not the most efficient conversion to the ethanol, and it produces a clear, direct economic competition between food and fuel that you want to talk about national security problems. Just think about that one for a while. Transportation choices. I'll bet all of us in 20 years are going to be driving something, well, gee, maybe like this. I highly recommend it. I think I'll make it to, well, I don't know if I should guarantee about tomorrow. I still believe in weather forecasts, and I've fallen 3 times on ice, and so I'm not getting any younger. But I think we're going to have some very clear choices in the kind of transportation we have. Now, everybody under 30, you can go to sleep for this one. But everybody over about 40, wake up. And I want you to think back. I want you to think about what an iPhone does. And I want you to think back when you were in college. And if I would have walked up to you and said, there's going to be a little gizmo you can put in your pocket and it'll do all those things, you would have flat said, false. That is absolutely impossible. Think about it. You would have. That is just a miracle compared to what we had for technology. There's our technology of the 70s. We all recognize those. And think of what an iPhone does now. Well, we have to do the same thing for energy in the next 40 years. It's as simple as that. The kind of things we do now, burning train loads of coal to produce electricity, driving 20-mile-per-gallon vehicles, just isn't going to fly 40 years from now. I hope in 40 years some of you students are up here talking and laughing about how primitive our energy was back in '07. I hope that's true, because that's the kind of revolution that we've got to do in the next 40 years to get out of this. And let's hope some total miracles come out the way iPhones and all that technology has in the last 40 years. So what we need right now, first off, are some politicians that are willing to admit that we're in a big pickle and this isn't going to be easy, and maybe American society might have to even do a little bit of sacrificing here and there. And not one of them is willing to say that. They're willing to talk about new technologies and all that, but you say they keep real far away from talking about any fundamental change in American lifestyle, and we don't see how that can add up. Just doesn't add up. And while I'm really on the soapbox, my favorite, and I'm sure this will get me run out of town within minutes here, is I think a progressive carbon tax is the best thing we could do. And this is a serious tax, $1 per gallon per year, going up $1 each year. So that means what? $8 a gallon gas in 5-6 years? I don't think any of us can think about without kind of going, but that's what we need. That's what we need to get people to pay attention, that this is for real and we got to get to work. Now, what's the purpose of that tax. It actually isn't, in my view, to collect money. That's how naive I am. That's why I'm a professor and not a politician, is I have no clue what to do with extra tax money. And so all I'm looking at is social engineering and not revenue enhancement. But what we need, higher energy prices will help emerging energy technologies mature. There's nothing that could ever get going when oil was $10 a barrel. That's the biggest energy steal of all time. And that's why we used it up as easily as we did. But what we've got to do now is provide the incentives so new energy technologies have a chance to get going. And the best way to do it is make the energy valuable enough that they can see that they can compete against the current energy producers. And we got to discourage consumption. I mean, at $8 a gallon, boy, would we discourage consumption, wouldn't we? It would work. And I'd have to say, all the cap and trade ideas I'm seeing sound like a big monopoly game for the Wall Street sharks. And they're going to have great fun making zillions of dollars, and they're going to forget about the climate part of the deal. And that's why I'm not a big fan of cap and trade logic at all. And a tax that every single person that was paying, that was using carbon-emitting energy would get everybody's attention instantly. I mean, this is, I think, free market economics. Well, kind of. I never did take an econ course, so I might have that a little bit backwards. But I think you all get the point that if energy costs more, we would very rapidly get incentive to use less. And in fact, we traded in an 18 mile per gallon car last spring for a 50 mile per gallon car now, so we're using less gas now than we did a year ago. And so a lot of these are just choices that we make as consumers as to what to buy next. It isn't necessarily that we're going to spend any more money on energy. We might, but we might just choose different options to use less, and our net energy cost might stay the same. But it would really focus your attention on energy use. And of course, the other part of the issue is show the true cost of carbon fuels. Right now, we are using the atmosphere as a free garbage can. We learned this with water pollution 40 years ago, didn't we? That you can't just dump stuff in the river forever and without it backfiring sooner or later. And now we're learning it with the atmosphere and with carbon, and it's the same principle. If I haven't made enough enemies yet, I'll try even harder to get everybody mad. One of the easiest ways you can save energy is drive slower. Just about every car on the road gets 3 to 5 miles a gallon better gas mileage at 65 than it does at 75. You can't read this graph, but there's a Prius on here, there's a Mercedes on here, I think there might be an F-150 pickup. No, these are all European. But the point is, it's simple physics of aerodynamic drag. And going faster just burns more gas. So there's your easy first step that doesn't cost you a nickel. But I actually think with a little bit more focus than society has now, I think within a decade or so, we're going to have an array of technological options that will be sufficient, if we choose to get us out of this. And just the point of 50 mile per gallon hybrid cars that already exist, who knows in 10 years what these already are around. And so I think the technological options are on the way. And a little bit of carbon taxing to give them that incentive, I think, would bring those to the fore faster. What I do not see is how we're ever going to get the international leadership and cooperation to make everybody in the world cooperate in the way necessary. And of course, right now, they're all waiting for us. You remember that curve. We're the very top emitter by far, and they all know it. So until we do something, we can't expect any other country to do a thing. And they're actually already doing a fair bit, but we have to start leading on this. We already know how ineffective the United Nations is now. How do you propose to get international governance on this? As I say, this is becoming a political science question, not a climate science question. And how we're going to make this happen, I'm clueless. I'm coming over to the other side of campus. But I will say that being at a university is an awful good place to be. When you have this kind of social revolution on the way, the lead thinkers are often in the university. So I would say to the students in the audience, you're going to have a good job market, that's for sure. If you're in the right majors, there's going to be an awful lot of new stuff happening, and it's going to come at us so fast that us oldsters just can't change fast enough. So you're going to win for sure. I mean, I already, when friends show me their iPhone, and I kind of, let's see, I think about 3 of the 12 functions I'm able to actually do. And I think, here we go with energy. So it's a very good time to be a college student. But you're going to have to be ready for some wild change similar to what we've had in information. I mean, think back to that 1970s to 2007 information and translate that to energy. And so you were wondering if I was ever going to get to the title. What's this phony title this guy had for this talk? And so over the years that I've given this talk, I've seen lots of responses. And I finally started about 6 or 8 months ago working on this. So this didn't come out overnight. And from the 5 stages of grief that were very famous, developed by this Elizabeth Kubler-Ross in the 70s. And I thought, I wonder if this fits. And so as I started going through it, this is the short summary. The deniers, boy, do we know there's some of them still around. If you read the Missoula Independent, they're still teeing off on me. Not to mention Al Gore. We were related to, who was it? Stalin and Lenin a couple weeks ago. And of course, the next to anger, I get hate mail nowadays. I get anonymous letters with no return address and no signature. So there's definitely people that are mad about this. They don't want to hear what I'm saying. There's the bargainers that say, well, it was always too cold in Montana anyway. Didn't you say our growing season's getting better? What is the problem? And of course, they still are saying, I don't want to change what I'm doing. Well, an awful lot of people hop to step 4, there's no doubt about that, of depression. We're in a bigger pickle than we can get out of on this one. And it's awful hard to not fall into that on a regular basis. Because I sometimes think this issue is so big that none of us can actually get our head all around how serious this issue is for humanity. But what we really have to get to in order for some action is to step 5. We have to accept that this is the world we now live in. We have to understand that we're going to have to make some big changes. We need to understand that we have to help those changes get started, and that if we do, that by the end, we really can wiggle our way out of this. But these are changes that are not just around the edges. I hope I've convinced you. These are fundamental changes of certainly American lifestyle and ultimately global lifestyle that are unprecedented in human history. That's all. And so, but we kind of don't have any choice. You remember that graph that shows the global temperature up to the top of the graph, and we just don't know if we have a functioning biosphere at that temperature. So as we sit here all today, I really hope that I've helped get you to stage 5 of, well, this is what we're in now, and we better just get to work, and we better be willing to make some uncomfortable choices, because this isn't all going to be comfortable. And yet, if we don't get to work, we don't know where the next 100 years are heading. That's it. Thank you.
Thank you, Steve, for a great lecture, for your work on behalf of the university, and for your work on behalf of the planet. Please, everybody, stay and join us for the reception, and stop and shake Steve's hand. Thank you for coming.